All right, so let's get into our first section of physics. Today we are talking about one-dimensional motion. So just some basic information here. One-dimensional motion is the simplest of all the motions that we're going to discuss. And when we say one dimension, we mean only along one axis at a time. So my object in this unit is either going to be moving horizontally or my object is going to be moving vertically. So only along one axis. You need to understand that motion is relative. So as we begin interpreting questions, we're going to start identifying our point of reference or our frame of reference, and that's going to be used to help us understand or address what direction my object will be moving and how that direction should be expressed in our math work. So motion is relative, meaning we need some sort of frame of reference. We are commonly going to be using the Earth as our frame of reference, which basically means that it's going to be very straightforward. There will be some occasions, though, where perhaps we have more than one object, and so we're going to say from this person or object's perspective or from that. So depending on where our point of reference is, that will determine what we are going to consider forward or backwards or the positive or negative direction. All right, this vocabulary word magnitude here is unofficially a vocabulary word for us in physics. A lot of times students do not fully understand what the word magnitude means. And so when they see it in a question, they don't understand how to interpret the purpose of that word within the question. So let's go ahead and address that right off the bat. The word magnitude is just a fancy word for number, or we are asking you to look at the value. Sometimes people say the size. Just be careful about choosing to use the word size. I don't want you to get that confused with volume. That's not the same thing. So for example, if we have a question that asks you to calculate the magnitude of the object's velocity, I'm asking you to give me the numerical value for that velocity. Okay, what is the number for that velocity? So that's what the word magnitude means. Okay, so when you hear that in the future, it just means we're calculating a value there. All right. Okay, so our first set of vocabulary words that you will need to know are distance and displacement. Now, initially, distance and displacement people assume are essentially the same thing. And if you're thinking, oh, yeah, they're both a how far, well, you're not wrong in thinking that they both are essentially a how far. But these two vocabulary words are technically two different meanings. And in my class, you are going to need to know the difference between those two. And those differences, although they may be minor, are going to affect how you answer questions both conceptually and mathematically. So distance is going to be how far something is traveled. If we are looking at this illustration here, the distance would be the actual physical path traveled. If you are wearing some sort of device that counts your steps, a step counter, or if we're driving a vehicle, the odometer is going to measure the distance for us. It doesn't matter what direction we move. It doesn't matter if we go around in circles. It doesn't matter if we're pacing back and forth or what direction we're moving. If we are physically moving, then that device is counting our distance or counting that motion towards our distance. So our distance is going to include all movement. Sometimes we identify it as the total path or total distance traveled because it's all the directions and motions considered. Looking at the illustration, the difference between distance and displacement is that distance considers all of the motion, direction, and details, whereas displacement is basically an overview or a summary. How did you get from point A to point Z? Sometimes we can visually see that displacement is the shortest distance between 2 points. Now, a lot of times people say A to B. I like to say A to Z because whenever you are being asked a question about displacement, we are saying what is that final position in reference to our initial position. So this is going to be one of those vocabulary words where the direction is important, okay? Displacement is the change in position and it must include a direction. So from this location, where is position Z? Well, we can identify a direction because we have a specific point of reference for that displacement. It's the shortest path from A to Z, so that's kind of a conceptual fact that you need to know. The displacement can either be positive or negative when we're just expressing this numerically. So to say that we have a positive or negative direction is to tell us, or a positive or negative value for our displacement is to tell us the direction according to that initial reference point. So in general, when we're talking about horizontal motion, we're going to say to the right will be expressed as a positive value and to the left will be expressed as a negative value. Speed and velocity are another pair of vocabulary words that you will need to know how they are alike and then what about them makes them different meanings. In general, they both are going to tell us a how fast, similar to how our displacement was both a how far. But just like distance and displacement, there is a slight difference between the two, and you need to know what that difference is. So speed is a measure of how fast something is moving. It says the rate at which distance is covered. I want to pause for just a moment here and point out whenever we see this word rate, then we are measuring the amount of time that it takes for something to happen. So we're going to have lots of definitions in the future where it's the rate of something. So in this case, our speed is going to be distance divided by time. So all the motion that takes place divided by the amount of time that it takes to complete that motion. Velocity is going to be different in that it now includes a direction. So velocity, instead of being defined as distance divided by time, we have to replace distance with the how far that includes the direction. So our velocity is going to be our displacement divided by time. Okay, both of them are going to be a rate of how fast. This is my distance in meters or displacement in meters and then divided by time. But if we're dealing with velocity, it has to specifically be that displacement so that we can either have a positive or negative velocity. So our formula here is delta V is equal to delta X over T. And let's take a moment to identify what all of these variables stand for. So the letter V stands for velocity, and that is going to be measured in meters per second. The letter X stands for our displacement, and that is going to be measured in meters. And when you are working on your practice assignment today, if you do not have the unit already in meters, unless the question says differently, you are expected to convert that distance or that displacement into meters before you plug it into the equation because it is written so that it calculates a value in meters, all right? And then our T is going to stand for time, and ideally that is in seconds, and once again on your practice work, if it's not, you'll need to make that conversion. So how are you supposed to know that velocity is in meters per second? Just from looking at the math work. Well, if we were to actually calculate a velocity over here, we would have some number to represent our displacement in meters. We would have some number to represent our time in seconds. And so when we look at our units, we're left with meters divided by seconds. So that's how we know velocity is supposed to be in meters per second for this calculation. In the What Math Review assignment, you were asked to perform some calculations and simplify those units. And so hopefully you've had some opportunities to figure out how that works so that you can then decide what the proper units are as you continue to work through the questions throughout this class. But if you need assistance on that, please feel free to reach out so that I can help you as needed. All right, so we know that displacement has a direction. We know that velocity has a direction, but how are we supposed to determine whether that should be a positive or negative number in order to represent our direction? So in this slide, what we're looking at is how we make that decision. When we look at this illustration, we have person A and person B. Person A is moving to the left, so you can see person A was given a positive value for his displacement. In this example, we're going to say that he moved 2 meters, so he has a positive 2 as his displacement. Person B is moving in the negative direction, so you can see that he was given a negative value for his displacement. So if velocity is displacement divided by time, Time is always positive. It's what we call a scalar value, meaning it has no negative, it has no direction. It will always be a positive number. There is no such thing as negative time, right? We know that. So if time is always positive, then when we go to calculate our velocity, velocity is displacement divided by time. So we're going to take the negative displacement for object A, and you see that that's going to give me, the positive displacement for object A, and you see that's going to give me a positive value for object A's velocity. We take the negative displacement for object B, and that's going to give me a negative value for object B's velocity. That's how we determine whether our value should be positive or negative based off of our direction. All right, if we take a moment and look at the three vehicles in the top right-hand corner of the slide, hopefully you see that their motions are different. In general, they are all starting from rest, and then they are moving so that they have some speed across the screen. Now, how quickly or how much time it takes for them to reach that speed is going to vary by car and even at different moments. For a particular car, how quickly or slowly that speed changes is going to vary from car to car. If we look at the image in the bottom right-hand corner, we have a woman who is sitting with her foot on the gas pedal. Now, if we assume that she is pressing down on the gas pedal, then we understand that she is causing her speed to change, right? So when we look at these two images, my question to you is, are all of these objects experiencing an acceleration? The three cars at the top and the woman in the bottom, are these objects experiencing an acceleration? And the answer to that is yes. Now, if I say that the woman, instead of having her foot on the gas, moves her foot to the brake and she presses down on the brake, is she now experiencing an acceleration? And so here's where I sometimes get different answers. Let me tell you, the correct answer to that is yes. By definition, acceleration is a measure of how much the velocity changes as time goes on. So on this slide, I put the word change in italics. It is important. It's a rate of change in velocity. The definition does not dictate what kind of change has to be made. It simply states that a change in velocity has to take place as time goes on. So for all of these examples, whether her foot is on the gas or the brake, or if we're looking at the three cars up top, they are all experiencing a change in velocity over time, so they are all experiencing an acceleration. Now, often students want to tell me, well, if she puts her foot on the brake, then that is a deceleration. You are correct. In English, in the English language, we would say that she decelerated. But let's think about what the prefix D, this DE prefix, means at the front of our word. This is a prefix that gives the word a negative connotation. So when she moves her foot to the brake and presses down, she is causing her object to change its velocity such that the value is a negative change in velocity. So in this case, this is an acceleration. It's just a negative acceleration. And you will be asked questions where you need to understand acceleration is change in velocity over time, period. You will be asked questions where you need to know whether it's a positive or a negative change, okay? And then what if the velocity does not change at all? Well, if we have an object that is moving at a constant velocity, where the velocity or the speed does not change at all, then that object is not accelerating, okay? The formula for acceleration is going to be the change in velocity over time. So when we look at our formula, we have our acceleration is equal to the change in velocity over time, or I'm showing you in detail here how we would go about calculating the change in the velocity and how we would calculate the change in our time. Our units here are going to be meters per second squared. So let's take a moment and review how we come up with those units. My velocities should be in meters per second. My time should be in seconds. So after I've performed my calculation, I should have meters per second, which we would simplify as meters per second squared. Let's talk about some of those additional symbols that we saw on the screen there. So some of the formulas that you've seen so far, some of these variables have little arrows over the top of them. I want you to know that these arrows are all here to indicate that that particular variable is a vector. So what does the word vector mean? What is a vector? Well, let's pause and think. What does an arrow illustrate? An arrow illustrates direction. So a vector is a category or a classification that we are going to put some of our variables in. Any variables that we discuss where that particular variable includes a direction, we would classify it or categorize it as a vector. So we have discussed displacement as a vector because direction is important. We've discussed velocity and acceleration all as vectors. So as we have gone through these slides, you've noticed that there have been, or maybe you haven't, but go back and look, there are some arrows over some of these variables, and that's because those are variables that the direction is important. Now, as we continue through the class, if I am writing this information down, I personally choose not to draw my vectors over my variable symbols in my math work. I personally am a visual processor, so the way that things look, the way that it's organized and laid out, does affect how I process that and my ability to work through it. So I personally choose to leave off the vector symbol just because I like less clutter in my math work. You are more than welcome to continue using the variable symbols with that vector illustrated above. That is your choice, but you need to know what a vector is and which variables are going to be classified as vectors. Let's talk about this little triangle symbol. So this triangle symbol in math class would be pronounced delta. And if we are calculating for delta, then I need you to understand that we are asking you to calculate the change. So in this class, you've already seen delta a few times. And so what that means is the variable that we are discussing, the variable that follows that delta sign, we need to calculate how much that particular variable has changed. So how would you go about calculating the change in a math class? Well, I'm going to pause and let's pretend that we were in math and we were looking at a graph. If we're looking at a graph in math class, let's say that we're calculating the slope, and that's going to be my rise over run, which is going to tell me how much my y value changed divided by how much my x value changed. And in math class, you would calculate that by saying y2 minus y1 over x2 minus x1. What's the purpose of giving you the format that y2 is the first value and y1 is the second value? Well, it's going to change how you calculate that answer. You need to follow it, plugging in your values in this order so that it gives you the correct increase or decrease in the y value along that axis, right? Well, it's the same thing in this class whenever we're calculating the change, except instead of saying y2 and y1, we're going to use these subscripts f and I. So f stands for final, I stands for initial. So whenever we are calculating the change in our velocity, we need to subtract so that we take the final velocity minus the initial velocity. It's really important that you put these numbers into your calculator in this order because it will be the difference between a positive value for velocity and a negative value for velocity. And since we are talking about how that velocity has changed, this will indicate an increase or a decrease. And remember, velocity is a vector, so then that direction also comes in, right? So there's lots of little details that are going to affect your final answer, how you interpret things, how you calculate things. So as you're moving through your practice work, be careful that you are taking the time to work through the details and understand how those details affect your answer. All right, what I want to do at this time is work through a couple of derivations. Now I want to pause real quick and I want to tell you that you have the choice right now as you're working through your practice work to decide whether you want to manipulate your formula for your unknown variable and then plug your numbers in, or plug your numbers in and then manipulate your formula. When you're doing your practice assignment, whenever we're working through math problems, I want you to follow the guess process. And if you don't know or if you don't remember what that was, you need to go back and reference my How to Math video. In that video, I talk about how I want you to show your work using this process so that you can get full credit in my class. So the big idea here behind the guess is that it's a specific format for you to follow, a template, if you will, so that you can organize what information you have to work with, so that you can determine what formula to use, so that you can correctly put the numbers where they belong to calculate your answer. So you have the opportunity right now to, once you've identified your formula, plug your numbers in and then do your algebra. But I will let you know that in the future, in the near future, you are going to be required to do some algebra without numbers because you don't have enough information to perform the calculation with numbers plugged in, or when we get to the part where I need you to derive formulas for me, like I'm about to demonstrate, the whole point is to recreate a new equation without having any numbers provided. So I'm going to walk you through a couple of examples. You will have the opportunity to go back and review this on the PowerPoint that is posted on my website. When you go to that PowerPoint in Canvas, you will have some slides that are blank like this is now, and then there's also going to be a couple of slides where they're worked out in detail. Don't stress if you are not ready to do the derivation without numbers just yet, but I wanted to take this opportunity to show you how that looks so that you can begin practicing manipulating your formulas. So when we get to the unit where you have to derive it without numbers, hopefully between now and then you've worked on it and you'll have a better base for being able to do that when it's time. Okay, so this first example, we are going to derive the equation VF equals VI plus AT. And right now, the only formulas that we have are V equals delta X over T and A equals delta V over T. So we're going to use the acceleration equation in order to help us derive the formula at the top. All right, so looking at this formula, A equals delta V over T, let's just take a moment to review what we're supposed to know about what this equation means. This equation means that I'm going to calculate my acceleration by finding the change in velocity. And so we're going to do that specifically VF minus VI, final minus initial. That's how I calculate my numerator. And then divided by, and then in the denominator, it says delta t. Now, time is time, and a lot of times in our math problems, we're just going to tell you how much time. But if you guys are performing a calculation off of a graph, or maybe it's a word problem where we've given you a sequence of events at different moments of time, make sure that you are only using this segment of time in question for your calculation. So it is still a change in time. There's just only certain circumstances where you have to actually go and subtract this time minus that time to get your time fragment, okay? So I'm going to choose to just write the letter T, and I'm going to leave off the delta because I like for my formulas to be clean of extra markings. And so if I am trying to solve for final velocity, I simply need to follow my algebra steps in order to get V off all by itself. So the way that I'm going to do that is, first off, I'm going to recognize that the change in velocity collectively is my numerator. And then all of that is being divided by time. So the first thing I need to do in order to rearrange this equation is to move my time variable. So I'm going to multiply by time on the right. I'm going to multiply by time on the left. So time is now gone from the left. I'm sorry, from the right-hand side. And on the left, I have A times T is equal to VF minus VI. Now from here, VF and VI are being subtracted, so I'm going to add VI to both sides. So this equals 0 or cancels on the right. So the right-hand side leaves me with VF. On the left-hand side, I am simply adding whatever VI is to whatever acceleration times time was. And so that's how I end up with my new formula. Looking at our second equation here, I have the formula delta x is equal to VIT plus 1/2 AT squared. That's the formula that I want to derive. In order for me to perform this derivation, I'm going to need both of the equations. from today's notes. I'm going to need my acceleration equation and I'm going to need my velocity equation. So let's start off with the acceleration equation. Here we have already decided that acceleration is the change in velocity, which is Vf minus Vi over t. And looking at my derivation end goal, I see that there is no final velocity in that formula, which means that somewhere along the way, I got Vf to disappear. So what I'm going to do is I'm going to go ahead and take this formula and the derivation we just did where we rearranged it to solve for Vf, I'm going to go ahead and write that down here. We could go through the steps again, but shouldn't be necessary at this time. So acceleration times time plus initial velocity is going to be equal to my final velocity. And I'm going to let that sit there for a second. Over here on the right hand side, the change in velocity over time, is equal to my displacement over time. I want to pause for a second. On one of the previous slides, we said that this is also how you would calculate your average velocity. So this formula can also be the formula to use if you have a question that asks you to solve for the average velocity. If we were in math class and you're being asked to find the average of a data set, you would simply take the values that you were given, add them up, and then divide by however many values were included in that calculation, right? So for this particular formula, my delta V specifically represents my final and my initial velocity. So if we are averaging this, we are going to say VI plus VF, because those two things are being added together, and then we're going to divide by 2, because we only have 2 values in that average, right? So average velocity is VI plus VF divided by 2, and that is equal to my change in position or my displacement over time. Okay, now from here, this particular question is asking me to solve for my delta x. So I'm going to need to manipulate this formula in order to solve for delta x. Now, on the left-hand side, I want to go ahead and expand this so that I have individual variables that I can move around and rearrange as needed. So I'm simply going to rewrite this as 2 separate numbers where they're both being divided by 2. So I'm going to choose to write that as a 1/2. Okay, so I'm going to say that this initial formula can be rewritten as 1/2 VI plus, and then I said that in my derived formula over here, I don't have a final velocity. So what can I do as I'm trying to expand my average velocity equation in order to get rid of that final velocity? Because this would be a scenario where in the word problem, the final velocity is unknown and they want me to solve for the displacement. So how can I solve for the displacement if my object experienced an acceleration and I only know the initial velocity? So in this case, what we would do is we would take this VF that we calculated before, and we're going to replace that piece in our formula. So this is going to go here, okay? So I am going to write in this VI plus AT in place of my VF. So this is supposed to be 1/2 VI plus 1/2 VF, but instead of using VF, I'm going to say 1/2, and then I'm going to apply that to the VI and the AT. Okay, so all I did was take this VF equals equation and I plugged it in right here, and then my initial formula said I was cutting everything in half. All right, so that is going to be equal to delta x over t. Okay, from here, we're going to do a little bit of simplifying. So when I look at my formula, I see that I have a VI here and a VI here. So I'm going to choose to add those up. We're going to add up our like terms. So 1/2 VI plus 1/2 VI is just 1 VI. So on the left, I have VI plus, I don't have anything I can do to simplify this AT, so I'm just going to say plus 1/2 AT is equal to delta x over t. Now delta x is what I'm solving for, so at this time I'm going to multiply both sides by t, so t cancels on the right, so delta x equals, and I'm going to multiply all of this by t, and I'm going to choose to go ahead and distribute this so that I have my final formula with everything separated out. So VI times t would be the first item, plus 1/2 a, and then t times t is going to give me t squared. So that is how we would manipulate these two formulas in order to give us delta x is equal to VIT plus 1/2 AT squared. Now, one more time, it is okay if you are not quite ready to do all of this work, okay? Know that this is something we are going to be asking you to do in future units. So as you work through your practice problems in this unit, when you can, go ahead and work on manipulating your equations before you plug your numbers in, even if that means you do some extra practice on the side just to work on that. Ask me for assistance as needed. You will eventually need to show me a derivation, and we will practice that again when it is time. I just wanted to take this opportunity to show you that if you are ever needing to rearrange a formula and you don't have all the numbers, or you want to manipulate it before you plug your numbers in, you simply treat every number like every variable like you would a number in math class, and you just follow your algebra rules to move things around, okay? I'm going to choose not to take the time to do equation number 3. If you really want to know what that looks like, then you can look at the PowerPoint that I have posted on my Canvas page and click ahead to that slide that shows you how it's manipulated. So here are all of your formulas laid out. I'm sorry, I don't know what happened with this equation right here. The way that's supposed to look is the average acceleration is equal to delta v over delta t. And if we were to expand that out, it's vf minus vi over tf minus ti. And remember, usually you don't have to subtract out your times, but in the event that you do need to perform that calculation, I wanted you to know what that looked like. Okay? All right. Please reach out if you have questions. Please make sure that you take time to practice according to the assignment that the agenda is asking you to work on each day so that you know what problems or what type of questions you need to ask me whenever we have the opportunity for questions during class.